In the last video, we looked at how to do three-dimensional rotations in geometric algebra. But how do we calculate rotations in higher dimensions? What even is a rotation in higher dimensions? We'll start to explore these ideas in this video. This video is a part of From Zero to Geo, a series where we formulate geometric algebra, an incredibly powerful branch of mathematics, from the ground up. So how do we calculate 4D rotations? Unlike in the previous video, the answer here is quite straightforward. The way we calculate 4D rotations is the same way that we calculate 3D rotations, at least in simple cases. Wait, simple cases? We'll get to what I mean by that later. In 4D, we still rotate by using planes of rotation. We can rotate a vector w by 2 times the angle from v to u in the plane given by v and u by using a double sandwich, just like in 3D. And to rotate in a given plane by an arbitrary angle, we can still create a rotor using a complex exponential involving theta over 2 and then use a rotor sandwich product. But this is all just an algebraic description of 4D rotations. What do they actually look like geometrically? While visualizing 4D rotations is impossible for us, we can use imperfect 3D visualizations to try to get an idea. We will try to understand 4D rotations by looking at the 3D projection of a rotating 4D object. But before we do that, I want to look at the 2D projection of a rotating 3D object to show off some of the important features of this projection in a situation that we are more familiar with. Here is a cube. To make things easier to describe, let's move the camera so that 2 of the 3D axes are lined up with the 2 2D axes. Now, the front face and back face of the cube are too close to each other, so let's increase the field of view while zooming in a bit. While we have been thinking of this as a 3D object, think about what this looks like as a 2D object. We have a smaller square inside a bigger square. Cubes have 6 square sides, but in 2D we only have these 2 squares. The other 4 square sides got morphed into these trapezoids. While the imperfect projection makes them not look like squares anymore, in 3D, they are true squares. Interestingly, while in 3D these 4 lines connecting the corners are all pointing in the same direction, in 2D, they are all pointing in different directions. Even though the projected lines are going in different directions, in the original object, they are all going in the same direction. Furthermore, even though all of the line segments in this picture have different lengths in the 2D projection, they all have equal lengths in the original 3D object. To make things easier to follow, I will keep the 2D basis vectors up here on the top. We can see that these 4 lines are going along the x direction, these 4 lines are going along the y direction, and while we can't draw E3, these 4 lines are going along the z direction. Let's now start rotating the cube. We can rotate it in the E12 plane, producing what looks like a 2D rotation. But in 3D, we have 2 other basis bivectors, E13 and E23. When we rotate in them, the 2D projection starts looking crazy. It may be hard to see because you are still thinking of this as a 3D cube, but try to imagine this as just a 2D picture. The squares in the middle and outside start morphing to become the trapezoids on the sides, and the trapezoids morph to become the squares. It can look even stranger if we start rotating in non-axis aligned planes, but in this video, for the sake of simplicity, let's keep our rotations axis aligned. In 2D, this is quite a strange looking process. It's important to recognize that this strangeness is purely an artifact of the projection from 3D to 2D. In 3D, this rotation looks pretty normal. But in the 2D projection, things look weird. The same weird things will happen when projecting 4D rotations down to 3D, so keep this in mind. The reason our pictures of 4D rotations look weird is purely a result of the projections we are forced to use, and they are not weird features of 4D rotations themselves. Let's now move on to a 3D projection of a 4D object. We were just looking at a 3D cube, so let's now look at a 4D cube, also known as a tesseract. It may not look familiar, but bear with me for a moment. To try to make this easier to understand, I will be showing the tesseract on the right side of the screen, and I will also show a cube on the left side of the screen going through similar transformations as the tesseract on the right. One thing that's confusing about this presentation of a tesseract is that there are actually 2 projections happening. One is a 4D projection down to 3D, and the other is a projection of that 3D projection onto a 2D screen. I'm actually using different camera positions for each of these projections. Currently, both cameras are viewing this tesseract at an angle. I'll keep the 3D camera in the same position and orientation because I think that this position helps us see the 3D projection the best. However, we'll move the 4D camera around similarly to how we move the 3D camera around with the cube. So, like in the 3D case, let's move the 4D camera so that 3 of the 4D axes are lined up with the 3 3D axes. Now, the front and back cubic faces of the tesseract are too close to each other, so like before, let's increase the field of view while zooming in a bit to make the distinction more clear. In 3 dimensions, the picture here looks like a smaller cube inside of a bigger cube. While cubes have 6 square sides, tesseracts have 8 cubic sides. Like when viewing a cube in 2D, we only see 2 of these sides as cubes. The other 6 cubic sides got morphed into these trapezoidal prisms. While the imperfect projection makes them not look like cubes anymore, in 4D, they are true cubes. These 8 lines connecting the corners are all parallel to each other in 4D, despite the fact that they are pointing in different directions in our 3D projection. Like in the 3D case, even though all of these line segments have different lengths in this projection, they all have equal lengths in the original 4D object. To make things easier to follow, I will keep the 3D basis vectors up here on the top. We can see that these 8 lines are going along the x direction, these 8 lines are going along the y direction, these 8 lines are going along the z direction, and while we can't draw E4, these 8 lines are going along the 4th direction, often called W. Anyway, with all of the setup done, let's finally look at how this picture changes under a 4D rotation. First, we can rotate in the familiar 3D planes E12, E13, and E23. These rotations don't look that weird. However, in 4D, we have 3 more basis bivectors, E14, E24, and E34. Rotating in one of them, we get something that looks much crazier. Again, the reason this looks crazy is the fact that we are doing a projection, and it is not a feature of 4D rotations themselves. If it were possible to see this image in 4D, it would look as simple as the rotation of a cube. Right now, we are rotating in the E14 plane. Remember that when rotating in a plane, the vectors in that plane change, while the vectors perpendicular to that plane do not change. We can see this in the 4-dimensional rotation here. Notice that one of the line segments originally going along the E1 axis ends up becoming a line segment going along the E4 axis, which then later becomes another line segment going along the E1 axis. Meanwhile, the lines going along the E2 and E3 axes don't change direction. Again, this is just like how rotations in lower dimensions work. The vectors in the plane of rotation rotate, while the vectors perpendicular to it are not changed. And, for the sake of completeness, here is a rotation in the E24 plane, and here is a rotation in the E34 plane. I want to now look at 4-dimensional bivector exponentials in more detail. Whenever a bivector squares to a negative scalar, we can use Euler's formula to exponentiate it, even in 4 dimensions. In lower dimensions, all bivectors square to negative scalars, so in those contexts, Euler's formula is valid for all bivectors. However, in 4 dimensions, we have an issue. Consider a bivector like E12 plus E34. It squares to -2 plus 2E1234. This isn't even a scalar, so Euler's formula no longer applies. If we want to exponentiate this bivector, we can't use Euler's formula. So how can we calculate this exponential? One idea you might have is to use Euler's formula on E12 and E34 separately and then use one of the exponential identities to calculate the full exponential. The problem here is that this identity actually fails when exponentiating bivectors. We can see this in 3 dimensions by considering E12 and E23. If we calculate e to the E12 plus E23, the result is not equal to e to the E12 times e to the E23. When actually proving this identity, a vital assumption that you need to make is that AB is equal to BA. This is true in the real numbers, but not always in geometric algebra. However, even in geometric algebra, if you are in a case where AB is equal to BA, you can use this identity. Going back to e to the E12 plus E34, We're in luck. E12 and E34 do in fact commute, so despite what I said earlier, we can calculate this exponential by using this identity, calculating each exponential separately, and then multiplying the results. Notice that this rotor has a 4-vector part. This is notable because the two ways of creating rotors that we have seen up until now could not create rotors with a 4-vector part like this. The product of two unit vectors is always the sum of a scalar and a bivector, and the exponential of a bivector that does square to a negative scalar is the sum of a scalar and a bivector by Euler's formula. So how should we interpret this rotor? Usually, when doing a complex exponential, the plane of rotation is the bivector that is being exponentiated. But remember, we saw in a previous video that E12 plus E34 doesn't represent a plane. However, it is the sum of two planes, E12 and E34, so we can think of this rotation as having two planes of rotation, E12 and E34. And this idea of a rotation having two planes of rotation is not just algebraic. Here is what it looks like to rotate by this rotor. If you look close enough at it, you can see that the rotations in E12 and E34 are happening at the same time. This kind of strange rotation arises because E12 and E34 are completely perpendicular. This geometric fact is the source of many of the oddities that we see in 4 dimensions, including how E12 plus E34 is not a plane as we saw in Chapter 2, and that the rotation generated by E12 and E34 simultaneously is not a normal rotation. Recall from Chapter 2 that the bivectors that do represent planes are called blades. We also call them simple bivectors. We can extend this simple terminology to rotors and rotations too. If a rotor can be written as the exponential of a simple bivector, we say that the rotor is simple as well. If a rotation is represented by a simple rotor, we call the rotation simple too. Rotations such as the one created by exponentiating E12 plus E34 are not simple rotations. In this particular case, because we are rotating in two planes, we call this rotation a double rotation. It turns out that the rotation generated by E12 plus E34 has another oddity as well. While we saw that E12 and E34 can be considered to be the two planes of rotation for this rotation, there are actually other pairs of bivectors that generate this rotation too. For example, the bivectors E12 plus E14 minus E23 plus E34 over 2 and E12 minus E14 plus E23 plus E34 over 2 are simple and completely perpendicular, but their sum is equal to E12 plus E34. This means that these two different pairs of bivectors create the same rotation. In fact, for this particular rotation, there are an infinite number of pairs of planes that generate the rotation. This is a notable departure from 2 and 3 dimensions where each rotation has a unique plane of rotation. Now you may think that all double rotations have an infinite number of pairs of planes of rotation, but this is actually not the case. It's not too important for us to know, so I won't go into a proof, but this only happens when the angles of rotation in both planes are equal. To differentiate this case from other double rotations, we call double rotations where both angles are equal isoclinic rotations. In an isoclinic rotation, we have an infinite number of pairs of planes of rotation, but in all other double rotations, we have one unique pair of planes of rotation. We just covered a lot of different kinds of 4-dimensional rotations, so let's summarize what we have learned. Given any simple bivector, exponentiating it produces a simple rotor. The simple rotation this rotor represents has a single unique plane of rotation. Given any non-simple bivector, exponentiating it produces a non-simple rotor. The non-simple rotation this rotor represents has two planes of rotation, so we call it a double rotation. If the angles of rotation in the two planes are equal, we call the rotation an isoclinic rotation, and the two planes of rotation are not unique. If the angles are not equal, the rotation is not an isoclinic rotation, and the two planes of rotation are unique. So what about rotations in dimensions higher than 4? Thankfully, there aren't any more major complications in higher dimensions that I know of. We can still generate simple rotations in the same ways as before, and we can get other non-simple rotations by exponentiating more complex bivectors. Starting in 6 dimensions we can get triple rotations, in 8 dimensions we can get quadruple rotations, and so on, although I haven't seen these names used too much. However, looking at some of the weird examples of 4-dimensional rotations, you may be wondering, what even is a rotation? We thought that we could create all rotations using simple rotors, but we now see that there are more complicated rotations. Have we even found them all? How can we make sure we can build all of the different kinds of rotations? We'll answer these questions in the next video.